Bacteria are very intelligent, and what happens clinically is when a new antibiotic is introduced, usually like 10 years later, you begin to see resistant strains of bacteria to that antibiotic. And if you look out on a timeline from like penicillin all the way through the newest antibiotics were developed in the mid-2000s, you kind of see this trend. And so we're constantly waging this war with bacteria, and they have the capacity to change faster than we do. So the importance of new antibiotic drugs is such that we're running out of the ones we already have. The riboswitch that I look at is used by gram-negative bacteria in a family called gamma proteobacteria. So it includes E. coli, another thing, Enterobacter cloacae, which has been in the news. It's actually on the CDC's type of most wanted list for a dangerous infection. There's also Klebsiella. Antibiotics they have always defined mechanisms, and some of them, like the penicillins, go after the cell wall of bacteria. Other antibiotics bind the ribosome within bacteria, which is the protein factory of bacteria. And this would be another way to stop protein production, but looking at it from another angle. The riboswitch is a mechanism that binds a compound. And in its natural state, the compound is something found within the cell, and it binds it very specifically. And the binding triggers the on-off type of switch, and usually being off, so you can turn off a set of genes. And in the literature, these genes have been tied to virulence, biofilm formation, all sorts of things that if were able to take that away from bacteria, it would make them less effective at their job.